Okay, hello and welcome back everybody. This is going to be the worked example section for inner products, norms, and orthogonality. I just want to start off by recalling the definition of the inner product. So given two sequences, let's say AK, K is an I, some index set, and BK, K is an I, the same index set. The inner product of the two sequences is denoted by the angle brackets that we place the one sequence in and the other sequence. And it's equal to the Einstein summation of the two of them with a conjugate on the second term, which can also be written as a sigma sum, AK, BK with a conjugate on the second term. Now that is still the most abstract version of these. We don't want to forget that for vectors, maybe for vector representations, we'll say, where maybe I can write it as A1, A2, A3, B1, B2, B3. We also write this a lot of times as a dot. So we'll write A1, A2, A3 with a dot, like a multiplication, B1, B2, B3. And following exactly the above, what does this equal? This equals a sum of those multiplied together, plus those multiplied together, plus those multiplied together, where everything on the right-hand side gains a complex conjugate. So it'll be A1, B1 conjugate, plus A2, B2 conjugate, plus A3, B3 conjugate. And for functions, the inner product of f and g will be the integral over the domain, whatever the domain of f and g happen to be, of f of x times g of x conjugate dx. So this is really what we want to think every time we have inner products. I do want to mention, for vectors, when notated with a dot, right, the dot that we have here is a little multiplication. So when we notate it with a dot, many will refer to the inner product as a dot product. If you ever hear the word dot product thrown around, it's the same thing. They're referring to specifically the inner product on finite dimensional vector spaces. Okay, and then let's cover the definition of a norm. So, given really one sequence, let's just say A sub k, k is an I, the norm of the sequence is denoted by, actually it's denoted and computed by, this is really the definition, we use two strokes, sequence AK, k is an I, so two strokes, it's equal to the inner product of AK with itself, and then there's a square root. Or we can use Einstein summation to say this is A, K, conjugate. Or we can use sigma notation to say this is the square root of the sum of K in my index set of AK times its conjugate. But what do we know about a complex number times its conjugate is that that will always be the magnitude of a complex number, magnitude squared. And so what we recover is a bit of a shorthand on these norms. We should really always think about, if we have a norm of a sequence, we should really always think about it as the square root of the sum of every element in the sequence. If it's complex valued, then the magnitude squared. If it's real valued, then you can just go ahead and square everything. but it's always going to be, so norms are always the square root of all entries added in magnitude squared. So you're going to take the magnitude squared of every entry of a sequence, and then you're going to add all those together and then finish off with the square root. And so just like before, the inner product, maybe we'll say for vector representations, we can compute a norm maybe of something like a1, a2, a3 as the square root of the magnitude of a1 squared plus the magnitude of a2 squared plus the magnitude of a3 squared. And for functions, we can compute the norm of a function as the square root of the integral over the domain of the magnitude of the function squared dx. So there's a little bit of shorthand on maybe getting better at computing norms faster. You can use these bottom two ideas every time you want to compute a norm and maybe skip having to take the inner product of something with itself. That's usually just an extra step that you don't have to worry about. And finally, let's talk about the definition of orthogonality. This one's fairly straightforward, thankfully. We have given two sequences, AK and BK. We call the sequences orthogonal if the inner product of AK against BK is 0. And of course, you can compute the inner product explicitly and say, okay, that's equivalent to me saying that this summation AK BK conjugate is 0. And so maybe we'll say this again for vector representations. We'll say something like A1, A2, A3, and B1, B2, B3 are orthogonal if A1, B1 conjugate plus A2, B2 conjugate plus A3, B3 conjugate equals 0. We could say for functions that f and g are orthogonal if the integral of f against the conjugate of g dx over the domain equals 0. All good ideas to keep in mind. I will cover one other definition, and that's the definition of normalized or normal or normalization of a vector. So you say, given a vector, or equivalently a sequence, let's just call it V for now, V with a hat, even though it could be a sequence. Maybe I'll denote it as a sequence as well, V sub k. K is in some index set. We say V is normalized, or normal, if the norm, big surprise there, equals 1. So 1, of course, is a very special number. It's the multiplicative identity. And so it's a very useful situation to refer to vectors with norm 1, since the norm kind of refers to the distance from the origin. This would be distance 1 from the 0 vector. That's kind of what we think about. And hence, let's just go in 3 dimensions really quick. There's my 3-dimensional axes. If I start with, really the point in the middle is our 0 vector, the origin. And I consider the collection of all points that are distance 1 away. So let's say that's the x1, that's the z1, here's the y1 maybe. But then, we're talking about total distance, so actually the negative ones work here as well. Negative 1 in each direction works as well, and in fact everything that kind of interpolates all of those, all of the points that interpolate these ones here, what we end up with, and I think you can probably tell, what is this? This is the sphere of radius 1. Okay, so what this gives us the ability to recover in any number of dimensions is this gives us a notion of a sphere in any number of dimensions, including infinity. So there's nothing really requiring us to be in a finite number of dimensions if we just require that the norm of something is equal to 1. And so really more than the sphere, the unit sphere is what we have a notion of. But you could restrict anything to a fixed norm. Say the norm needs to be equal to 11, and then you have a notion of a sphere of length of radius 11. So this is what we call normalized, and the unit sphere is kind of the common sphere to talk about. And then a normalization of a vector is the process which takes any non-zero vector and gives a normalized or normal vector out, and in particular of the same direction. And it's really not too hard to compute. We compute this as, so a lot of times I will write a normalization, I'll denote it as v with a hat on top of it. And this will be a scaling of 1 divided by the magnitude of v times the vector v itself. So we're thinking basically some vector v may be not normal, can get turned into, this is normalization, can get turned into this new object just by dividing by its magnitude. And really dividing is the same as, scaling by 1 divided by its magnitude. Since what will the norm of this be? Well, it'll be the norm of this entire object. But this term, since it's a scalar, can pull out, and we get this times the norm of v, and of course the numerator and the denominator are the same and cancel and give me 1. So this object is, we can call it the normalized vector. So normalized vector of the original one, v. And I'll use this notion of a hat. A lot of people don't use that notion, so be careful, because just because I use that notion doesn't mean everybody does. Sometimes I will write that v hat, instead of writing it as a scalar times the original vector, I will just pretend like you can divide by scalars, which I think kind of makes sense. But just interpret that division, it's a vector on top, it's a scalar on the bottom. Interpret the division as what's happening earlier. So that's a normalization. That's going to set us up for examples today, because basically our examples, we will be asking questions about orthogonality and normalization, because that really gives us everything we need to know about inner products. So we're going to be studying inner products by really studying examples of normalization and orthogonality. So the first example I will ask is, are the vectors 1, 1, 1 and I, negative I, 0 orthogonal? So I've got two three-dimensional vectors here, and they're complex valued, so we'll have to be careful. To test if some vectors are orthogonal, we check if the inner product is equal to 0. So sometimes I'll just write dots in the middle of an inner product to refer to that we're putting some arbitrary terms in there. So we're going to check if the inner product is 0. This shouldn't be too bad, right? So I can take the inner product of these two. 1, 1, 1, I, negative I, and 0. I'm going to be reading across and making sure I take a conjugate of all these terms on the right. And what does that give me? It gives me 1 times negative I, because of the conjugate, plus 1 times positive I, again because of the conjugate, plus 1 times 0, which will give me negative I plus 0, which does in fact give me 0. Check mark. Yes, they are orthogonal. Let's look at maybe a slightly more complicated example. are the vectors 2 plus I, 2 minus I, 1, and I, negative I, 0, orthogonal. We're just going to do the same thing as before and check if the inner product is equal to 0. Just as before, 2 plus I, 2 minus I, 1, I, negative I, 0. We're going to read across, multiply each of those together horizontally, make sure to compute a complex conjugate on the right. What we're left with is 2 plus I times negative I plus 2 minus I times positive I because of the complex conjugate plus 1 times 0. And I'll have to distribute the minus I to both terms, plus I to both terms. I'm left with negative 2I minus I squared. So minus I squared is minus negative 1, same as plus 1, plus 2I. Then I have a minus I squared again, so I end up with plus 1 again, plus 0. And the i's cancel, but I am left with a final answer 2, which is very much not equal to 0. So these are not orthogonal. The next question of orthogonality is going to be with some functions. It's going to set us up for teasing the Fourier series. So this will be maybe a little complicated for you. Consider the functions e to the I times x and e to the 2i times x. And those are definitely the imaginary numbers in the exponential on the domain 0 to pi. Are these functions orthogonal? We're going to have to get clever, so I'm gonna throw a few things out to remember from both complex analysis as well as some earlier calculus. Let's recall from calculus that the antiderivative of e to the a times x dx, because of u substitution, you can prove that this antiderivative is always 1 divided by a, e to the ax, plus a constant. So if you go through the u sub procedure, you'll find out that that is 1 divided by a, e to the ax plus c. And we'll recall maybe from algebra the property that e to the a times e to the b equals e to the a plus b. So you can add exponents together so long as you multiply with the same base. It's important that those are the same base. And we'll recall from the complex numbers that e to the I theta equals cosine theta plus I sine theta. So these three properties here are going to be necessary for us to test if the functions we care about are orthogonal. That's e to the ix and e to the 2ix on the domain 0 to pi. So let's go ahead and test now. So we're going to test e to the ix, questioned about orthogonal against e to the 2ix, which, recall, since we have functions, we're going to be performing an integral. So this will be e to the ix times e to the 2ix conjugate dx. Right? Because we're not going to forget that if I just have fg, this is the integral over the domain, f of x conjugate of g of x dx. So that's where we're coming up with that entire term from. Now I did skip over the domain here. Let's see, our domain is 0 to pi. It's up there. Domain is 0 to pi, so we're going to do the domain 0 to pi up here. Okay, so what does a conjugate do? Well, it just replaces an I with a negative I. So I'm going to replace every I with a negative I there. 0 to pi, e to the ix, e to the minus 2ix. That's because I replaced I with negative I, dx. This will be the integral 0 to pi. Because of my exponent rules, that's my algebra right up here, because of all of that, what can I do? I've got a multiplication of two exponentials. That means that I can combine the exponents themselves, and I get ix minus 2ix dx from 0 to pi. If I simplify what's in the exponent there, that's one copy of ix minus two of them. I get e to the minus ix dx. And now I can find an antiderivative. The antiderivative of e to the ix, or e to the ax, would be 1 over a, so I have 1 divided by negative I, because a is negative I here, e to the minus ix, evaluated on the bounds 0 to pi. And this is confusing to evaluate. How do I evaluate that on 0 and pi? Well, I've got my lovely Euler's formula to help me out. So Euler's formula is going to tell me, hey, rather than evaluating e to the minus ix, I can evaluate, well, what is the version of theta here? Really, a negative x is playing the role of theta. So that term and that term will become negative x. And so we have cosine negative x plus I sine negative x on the bounds 0 to pi. If I plug in pi, I have 1 divided by negative I, cosine of minus pi plus I sine of minus pi. And if I subtract, plugging in 0, this will be cosine of negative 0 plus I sine of negative 0. It's always useful to not forget the unit circle when we're evaluating cosine and sine. So let's see, negative pi would be moving anti-clockwise a pi amount. So this is negative pi. Cosine would be the x value there. The x value is negative 1. The y value is 0. So cosine will be negative 1, sine will be 0. This will give me negative 1, sine will give me 0. And then if I look at the unit circle at 0, that's just right here. The x value is 1, the y value is 0. So I have a 1 and a 0, and I can evaluate as 1 over minus I times negative 1 plus I times 0. So I just have negative 1 here. Minus 1 divided by minus I. Now I have 1 times 0, or 1 plus 0. And so what am I left with? I'm left with 1 over negative I times negative 1. It's 1 over I minus 1 over negative I. So I can pull the negative sign out. I have I. So I'm left with 2 over I, or if I want to simplify, recall dividing by I is the same as multiplying by negative I. So we're testing about orthogonality here. So the real question is, were these two orthogonal? What did I need for things to be orthogonal? I need the inner product to be 0. And what I've just calculated is the inner product very much not equal to 0. Hence, I can spell not orthogonal. Let's do one more example, and let's actually work with the exact same collection of functions, but we'll modify the domain. Example, same functions, new domain. So r e to the ix and e to the 2ix orthogonal on the domain negative pi to pi. Well, rather than go through all of the same work that I just did, let's write out really quick that all I need to do is compute e to the ix, e to the 2ix, which is the same as before, e to the ix, e to the 2ix conjugate dx, but my domain's changed, right? The domain is now from minus pi to pi, and before it was from 0 to pi, so the only thing that's changed is right here. And how does that play a role with our previous calculations? There, 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 and where did that 0 end up? It ended up right here and here. So I can take a shortcut and jump all the way down to this line, except I'm going to replace those zeros with minus pi. I'll replace the zeros with minus pi. So I have 1 over negative I cosine minus pi plus I sine minus pi minus 1 over I, negative I cosine. I'm replacing 0 with negative pi, right? The lower bound is negative pi, so I have 2 copies of negatives. So it'll be the cosine of pi plus I times the sine of pi. Now if I look at my unit circle, the first 2 terms haven't changed, still negative 1 and 0. But my second 2 terms, I'm looking at the unit circle at pi now. So pi on the unit circle is me moving all the way around clockwise back over there. So I'm going to get x is negative 1 and y is 0 here, where the cosine is -1, and the sign is 0. Hence, if I simplify everything, what do I have? I have 1 divided by -I. Cosine is -1 plus 0 times I, so I have -1 here. Plus, minus 1 over -I times -1 plus 0, -1. If I simplify, what do I have? I have 1 over I minus 1 over I. So I end up with 0, and all of a sudden, since 0 is equal to 0, these are orthogonal over a new domain. So the same functions, but all I've done is change the domain, and we gain orthogonality. So just some new examples here. Very, very interesting to see. Let's check some notions of norms. So let's say, example, compute the norm of 1, 2, 3. Well, that's going to be the square root of 1 squared plus 2 squared plus 3 squared. And here I'm using that shorthand that we started with today. If I go all the way up to the shorthand on norms here, if I do the norm of a vector, I just look at each of the entries and I square them. So there's my shorthand on norms. So I'm looking at each of the entries and squaring them and then adding them together and taking the square roots. What do I get? I get 1 plus 4 plus 9, also known as root 14. Let's do the norm of 1 over root 2, -1 over root 2. This will be a fairly common two-dimensional vector you'll see this semester. So I'm going to take a square root of the first entry squared plus the second entry, -1 over root 2 squared. It's going to be the square root of 1/2, because I'm taking root 2 and squaring it. And then since I have a square of a negative sign, that cancels the negative sign, I just have another 1/2. So the square root of 1/2 plus 1/2 is just the square root of 1, which is 1. Hence, the vector 1 over root 2, -1 over root 2 is normalized. It has norm 1, which is what it means to be normalized as a vector. Let's do one example of maybe a complex magnitude vector. Let's give it 4 terms. So 2 plus I, -I, -I, and 2 minus I. Let's compute the norm of this. It's the square root. Since everything is complex, we need to use the magnitude squared on all of these. So we're going to do the magnitude 2 plus I squared plus the magnitude -I squared plus the magnitude -I squared plus the magnitude 2 minus I squared. And keep in mind, the whole point in using the magnitude is that the magnitude will get rid of, eliminate all imaginary terms. You don't just throw them out, but in producing the magnitude will eliminate all imaginary terms. So let's recall the definition of the magnitude really quick. Magnitude of x plus iy is going to be x squared plus y squared. So I'm going to look at the coefficients of the real and imaginary parts. So those coefficients are what I'm using, not the i's. So what this gives me is 2 squared, in the first case, 2 squared plus 1 squared. Now where did the 1 squared come from? That's the coefficient of I is 1. And then the second case, I get -1 squared, because the coefficient of I is -1. I mean, there's a 0 sitting around there as well, but I'm not going to include it here, because if I add 0 to something, it doesn't matter. The third case is -1 squared, and the fourth case is 2 squared plus -1 squared. If I go ahead and compute these, what do I get? I get root 2 squared plus 1 squared is 4 plus 1 is 5. -1 squared is 1. -1 squared is 1. 2 squared plus -1 squared is 4. Plus 1 is 5. So I end up with the square root of 12. Here's some good examples of computing norms of vector representations. Let's compute a couple norms of functions. Let's compute the norm of the function e to the ix on the domain. Keep in mind, functions are always paired with domains. Let's do this -pi to pi domain. So the domain -pi to pi, keep in mind, the norm is always the square root of the inner product. So I'm computing, or if I do my shorthand for functions, the square root of the integral of the function in magnitude squared dx. So in this case, the norm of e to the ix over that domain is the square root of the integral over the domain, so the domain is -pi to pi. And then I take the function, that's a magnitude, right? So this is e to the I x times e to the I x conjugate dx. And since the conjugate is showing up, it's going to take that I, replace I with negative I. Conjugate shows up, and I'm replacing I with negative I. I have e to the ix, e to the minus ix, dx. Now notice, I still have this whole idea of exponent rules, where I can add those together. Because they share the same base, I can add the exponents, and I have e to the ix minus ix, dx. And what is ix minus itself? That's just e to the 0 dx. And what is any object to the 0 power? It's just equal to 1 minus pi to pi of 1 dx. And what is an antiderivative of 1? It's just x evaluated at minus pi and pi. Or in other words, it's pi minus negative pi. The minus signs cancel, and I have root 2 pi as my magnitude. So what I've discovered is the magnitude of e to the ix on this particular domain is negative 2, or is root 2 pi. So let's go ahead, final example, and normalize two vectors. So let's normalize the vectors 1, 3, and e to the 2ix over domain 0 to pi. What does it mean to normalize? Let's recall. To normalize is to divide a vector by its magnitude for norm. So all we're going to do is we're going to grab this vector. We're going to say 1, 3 divided by the magnitude of 1, 3. And how do I calculate that magnitude? It's the square root of 1 squared plus 3 squared, which is also known as the square root of 10. And what I can do with this root 10 is I can distribute it to each element. And so I can rewrite this as 1 divided by root 10, 3 divided by root 10. I want to play the game with e to the 2ix over a specific domain. Well, that's going to get a little trickier because I do have to perform the norm of e to the 2ix over that domain. It's going to be the square root of the integral from 0 to pi, because that was my domain, e to the 2ix times its conjugate, well, the conjugate of e to the 2ix is going to be e to the negative 2ix, and then the exponential rules will add 2ix to negative 2ix, and we'll get e to the 0 again, and e to the 0 will be 1 again. So this is kind of the cool thing about all of these complex exponentials, is they always have complex magnitude 1. You're always going to find that out about them. And so when you're computing their particular magnitudes as vectors, your life gets fairly easy. This is the antiderivative of 1 is x, and I'm evaluating that between 0 and pi, so I'll have pi minus 0, and we'll find out that the magnitude is just root pi. And if I want, I could write this as 1 over root pi e to the 2ix. So that's the normalized vector over the domain 0 to pi. And this is just the normalized vector. We don't really have domains with vector representations. They don't worry about domains. Technically, their domain is their length. And the domain here is the fact. Domain is the set 1, 2, referring to the rows 1 and 2. We don't really worry about domains with vector representations too much. Anyway, I'm going to stop there. It's been a bit of a long video, but lots of fun stuff that we're doing. So I hope you like it. See you in the next one. Bye.